Bismillah ar-Rahman ar-Rahim. This is subject of General Science and lecture number 27. Today our topic is Van der Waal equation. The outlines of the lectures are introduction about Van der Waal equation, then real gases, and then real gas behavior, and then we will study about Van der Waals equation. First of all, real gases. What are they? Most gases behave ideally when they are held at low pressures and also at high pressures, at high temperatures. So any gas that exists is a real gas. Nitrogen, oxygen, carbon dioxide, carbon monoxide, helium, etc. Real gases have small attractive and repulsive forces between particles, and ideal gases do not. Real gas particles have a volume and ideal gas particles do not. Room temperature is considered high temperature. Remember that ideal behavior means that the gas molecules do not interact with each other. Only kinetic energy is present. Almost all gases are known to be real gases, since they deviate from the ideal behavior under extreme conditions where the temperature and or the pressures are very high. Therefore, there are different examples of real gases like nitrogen, oxygen, hydrogen, carbon dioxide, and helium. Here, what is meant by room temperature? Colloquially, room temperature is a range of air temperatures that most people prefer for indoor settings, which feel comfortable when wearing typical indoor clothing. Human comfort can extend beyond this range depending on humidity, air circulations, and other factors. The World Health Organization in 1987 found that comfortable indoor temperatures between 18 to 24 degrees centigrade, and that becomes almost 64 to 75 Fahrenheit. So they were not associated with the health risks for healthy adults with appropriate clothing, humidity, and other factors. For infants, the very elderly, and those with significant health problems, a minimum 20 degrees centigrade means 68 Fahrenheit was recommended. Temperatures lower than 16 degree, and that becomes almost 61 Fahrenheit with humidity above 65% were associated with respiratory hazards including allergies. So the World Health Organization's 2018 guidelines gave a strong recommendation that a minimum of 18 centigrade means 64 Fahrenheit is a safe and well-balanced indoor temperature to protect the health of general populations during cold seasons, while a higher minimum may be necessary for vulnerable groups including children, the elderly, the people with cardiorespiratory disease and other chronic illnesses. So the recommendations regarding risk of exposure to high indoor temperatures is only conditional. Minimum risk high temperatures range from about 21 to 30 degrees centigrade, means 70 to 86 Fahrenheit, depending on the region, with minimum acceptable temperature between 25 to 32 degrees centigrade. That becomes 77 to 90 Fahrenheit. So the temperature range or defines as room temperatures for certain products and processes in industry, science, and consumer goods. For instance, the shipping and storage of pharmaceutical, the United States Pharmacopoeia, National Formulary, USP-NF, defines controlled room temperature as between 20 to 25 degrees centigrade, means 68 to 77 Fahrenheit, with excursions between 15 to 30 degrees centigrade allowed, provided the mean kinetic temperature does not exceed 25 degrees centigrade. The European Pharmacopoeia defines it as being simply 15 to 25 degrees centigrade, and the Japanese Pharmacopoeia defines ordinary temperature as 15 to 25 degrees centigrade, with room temperature being 1 to 30 degrees centigrade and 34 to 86 Fahrenheit. Merriam-Webster gives as the medical definition a range of 15 to 25 degrees centigrade as being suitable for human occupancy and at which the laboratory experiments are usually performed. However, sometimes gas molecules do interact with each other, and interactions between gas molecules is more likely at low temperatures. High gas pressures, that is high gas densities. So this introduces potential energy into the picture. Now, what is polar molecule? Polar, here you can say that like here H2O, and this is partial changes on the molecules are attracted to each other. Molecules that have significant intermolecular attractions, aka polar molecules, may also interact with each other. The compressibility factor Z. We can use the compressibility factor Z to detect deviations of gas from ideal behavior in experiments, and Z is equal to PV divided by N or T, where Z is less than 1. Intermolecular attractions exist and gas molecules can feel each other's presence. Now here the term is used ideal behavior. The behavior of real gases usually agrees with the prediction of the ideal gas equations to within 5% at normal temperatures and pressures. At low temperatures or high pressures, real gases deviate significantly from ideal gas behavior. It also assumes that the force of attraction between gas molecules is zero. So, for a gas to be ideal, there are 4 governing assumptions. The gas particles have negligible volume. The gas particles are equally sized and do not have intermolecular forces, attractions or repulsions with other gas particles. The gas particles move randomly in agreement with Newton's law of motions. So which gas deviates most from ideal behavior? It is also good to know that ideal gas law assumes that the gas molecules have negligible, no size. Keeping that in mind, Xc is the largest of the bunch and therefore is expected to have the greatest division of the ideal gas when under high pressure or low temperature. Now the question is that how do you know which gas is more ideal? Generally, a gas behaves more like an ideal gas at high temperature and lower pressure, as the potential energy due to the intermolecular forces becomes less significant compared with the particles' kinetic energy, and the size of the molecules becomes less significant compared to the empty space between them. Compare three scenarios for gases in a piston. Now here you can see that the piston was at some distance. Now the gas molecules, suppose, are at random positions. They are at distance. But when we press the pistons, then molecules comes closer. And again when we press piston, so the molecules becomes very close to one another. At low pressure, the first piston shows a gas at low pressure, means volume actual is equal to volume ideal. Ideal gas law and KTG are obeyed. Now here again we see that medicals to high pressure. The second piston shows gas at mid-high pressures. At a volume decreases, some molecules sticks together effectively, reducing the moles of gas. Now V actual is less than volume of ideal. So the gas is more compressible and attractions dominate. Now here, ridiculously high pressure. The third piston shows a gas at really high pressure. The gas cannot move, and we see that it actually does take up space as our common sense might tell us. Now volume actual is greater than volume ideal. Here and here repulsions dominate. Then the compressibility factor C. More about the compressibility factor C. Here, by using C is equal to P is equal to BV divided by NRT, and at C is equal to 1 at y-axis, and pressure, atmospheric pressure, that was kept at horizontal x-axis. Then attractions dominate. Now here we can see that this line shows real gases and this line shows also the real gases. Repulsion dominates. Perfectly ideal gas behavior is there. The Van der Waals equation. Corrects the ideal gas law for real gas behavior. NRT, and this has become total equations like P is equal to nRT divided by V minus NB minus AN square divided by square of volume. The van der Waals constants A and B are experimentally determined for each individual gas. The VDW constant describes the strength of attractions with units L square atmosphere per square mole. The VDW constants B increases with increasing molecular size with unit L per mole. The van der Waals equations corrects the ideal gas law for real gas behavior. Now P is equal to nRT divided by V minus NB minus AN square divided by V square. Now here what is NB? This is correction for the volume taken up by the gas molecules. And what is V square? That is correction for the attractions between gas molecules. The actual pressure P is reduced by this amount compared to the ideal gas law. Now predict the relative size of the van der Waals constants for the following gases. H2 gas means hydrogen gas. This is very small and not polar. Sulfur dioxide gas, larger atmosphere and polar. And P is equal to nRT divided by V minus NB minus AN square divided by square of volume. Predict the relative size of the van der Waals constants for the following gases. Like hydrogen gas, this is very small and not polar. Sulfur dioxide gas, larger atmosphere but polar. The van der Waals constant A and B, VDW means van der Waals. Constants A and B would both be larger for sulfur dioxide gas. So, which gas would produce the lowest pressure with moles T and V constants? So, methane, and its formula is CH4. This gas means small molecules and not polar. H2O gas, this is small molecules and polar. And equation is P is equal to nRT divided by V minus NB minus AN square divided by V square. Now which gas would produce the lowest pressure with moles T and V constant? P is equal to nRT divided by V minus NB and AN square divided by V square. If methane means CH4 is small molecule and not polar, so this means that A and B are both relatively small. The value of A, that is equal to 2.25, and the value of B, that is equal to 0.0428. The gas should behave close to ideally. The H2O gas is also a small molecule. Then the van der Waals constant will be of a similar size. However, since water is polar, the van der Waals constant will be quite a bit larger. A is equal to 5.46 and value of B is 0.0305. So the pressure exerted by water will be lower than the ideal pressure. So if we take the summary, then we can say that real gases interact with other and take up volumes in the container. The Van der Waals equations corrects the ideal gas law for real gas behavior, and P is equal to N or T divided by V minus NB minus An square divided by V square. If the gas is under ideal gas conditions, the Van der Waals equation reduces to the ideal gas law, and that is equal to PV is equal to nRT. Now we take revisions of the main points that we have discussed. First of all, we have studied that what are the real gases. Almost all gases are known to be real, since they deviate from ideal behavior under extreme conditions where the temperature and or the pressures are very high. Therefore, we have taken some examples, like we have discussed examples of oxygen, hydrogen, helium, nitrogen, and carbon dioxide. Then we have discussed about room temperature. This is the range of air temperatures that most people prefer for indoor settings, which feel comfortable when wearing typical indoor clothing, and human comfort can extend beyond this range depending on humidity, air circulations, and other factors. The World Health Organization in 1987 found that comfortable indoor temperatures between 18 to 24 degrees centigrade were not associated with the health risks for healthy adults with appropriate clothing, humidity, and other factors. For infants, the very elderly, and those with significant health problems, a minimum 20 degrees centigrade was recommended. Temperature lower than 16% with humidity above 65% were associated with respiratory hazards including allergies. Then temperature ranges are defined as room temperature for certain products and processes in industry, in science, and consumer goods. For instance, for the shipping and storage of pharmaceuticals in the United States, and Pharmacopoeia National formularly defines control room temperature as between 20 to 25 degrees centigrade. Then we have discussed about some ideal behavior. So what is ideal gas behavior? For a gas to be ideal, there are four governing assumptions. The gas particles have a negligible volume. The gas particles are equally sized and do not have intermolecular forces. We can call it attractions or repulsions with other gas particles. So the gas particles move randomly in agreement with the Newton's law of motion. And we have discussed that it is good to know that ideal gas law assumes that the gas molecules have negligible or no size. Generally, a gas behaves more like an ideal gas at higher temperature and lower pressure. As the potential energy due to intermolecular forces becomes less significant compared with the particles' kinetic energy, and the size of molecules becomes less significant compared to the empty space between them. Then we have discussed one of the point about kinetic energy. You must know that in physics, kinetic energy of an object is the energy that it possesses due to its motion. It is defined as The work needed to accelerate a body of a given mass from rest to its stated velocity. Having gained this energy during its acceleration, the body maintains the kinetic energy unless its speed changes. So what is the formula for kinetic energy? We all know that the equation of kinetic energy is half mv square, where m is the mass and v is the velocity, and the velocity in this equation is squared, which means that it is exponential. That means that as the velocity increases, so you will be multiplying by a bigger and bigger number, and kinetic energy equal to 18 joules. So if we define kinetic energies, and we can say that kinetic energy of the body as the energy possessed by the body by the virtue of its motion. So when is the kinetic energy maximum? The kinetic energy is maximum when potential energy is maximum. This occurs when the velocity is maximum, then mass is at equilibrium position, and the energy possessed by the body by the virtue of its position, that is known as potential energy, and the energy possessed by the body by the virtue of its motion, so that is known as kinetic energy. So we explain potential energy also. Potential energy, this is the energy that is stored in an object due to its position relative to some zero positions. An object possesses gravitational potential energy if it is positioned at the high above or below the zero height. So what are the different types of potential energy? Different types of potential energies are gravitational potential, chemical energy, nuclear energy, elastic potential energy, that is also called spring energy, and electrical potential energy, especially in a capacitor. So what are the examples of potential energy? Mechanical potential energy means this is a raised weight, water that is behind a dam, a car that is parked at the top of a hill, a snowpack means potential avalanche, a yo-yo before it is released, river water at the top of the waterfall, a book on the table before it falls, a child at the top of the slide. So common types of potential energy include the gravitational potential energy of an object that depends on its mass and its distance from the center of the mass of another object, the elastic potential energy of an extended spring, and the electric potential energy of an electric charge in an electric field. So the unit of energy in the International System of Unit is the joule, which has the symbol J. So the term potential energy was introduced by the 19th century Scottish engineer and physicist William Rankine, although it has links to Greek philosopher Aristotle's concept of potentiality. So potential energy is associated with forces that act on a body in a way that the total work done by these forces on body depends only on the initial and final position of the body in space. So these forces that are called conservative forces, and can be represented at every point in space by vectors expressed as gradients of a certain scalar function called potential. Since the work of potential forces acting on a body that moves from a start to an end positions is determined only by these two positions and does not depend on the trajectory of the motions. There is a function known as potential that can be evaluated at the two positions to determine this work. Then polar molecules means this is a chemical species in which the distribution of electrons between the covalently bonded atoms is not even. So polarity is the description of how different the electrical poles of molecules are. Each atom has a certain electronegativity. Then we have discussed about compressibility factor. Like in thermodynamics, the compressibility factor is E, and also known as the compression factor or the gas deviation factor. This is a correction factor which describes the deviation of the real gas from ideal gas behavior, and it is simply defines as the ratio of the molar volume of the gas to the molar volume of an ideal gas at the same temperature and pressure. So it is a useful thermodynamic property for modifying the ideal gas law to account for the real gas behavior. Then we have discussed ideal gas law. Means the ideal gas law is also called the general gas equation. This is the equation of state of hypothetical ideal gas, and it is a good approximation of the behavior of many gases under many conditions. So this was all about this lecture. Take care. Allah Hafiz.